on the pattern. Like nothing canceled on this one, right? I didn't have a 2 on top and a 2 on bottom that canceled. This one I happened to have it happened to happen. Fourth derivative. So what happens now? Negative 3 comes out and hits that 2, right? Yeah. So should I put negative 6? No. Maybe I should leave it as negative 2 times 3. Why would I do that? Because it looks like the next derivative, a 4 is going to go out there. And the next one, a 5 is going to go out there. So what I'm building up out there is what appears to be a factorial. Now this is negative 2 times 3 over x to the 4th. When I plug in 2, negative 2 times 3 over, what, 16? You want to do another one? One more? Fifth derivative. What? 2 times 3 times 4? Because it's negative and negative. So 2 times 3 times 4, x to the negative 5, which is 2 times 3 times 4 over x to the 5th power. Plugging in 2 times 3 times 4 over 32. Do you have enough to see the pattern? Yes? As far as you need to make sure you're sure about the pattern. See, I think if you would have stopped here, you may have thought that just, look, the bottom just keeps going up. Like if you would have stopped there, you said, okay, yeah, and the next one's going to be 8, and 16, 30. What you would have never maybe seen is the factorial thing on the top happening. Maybe, I don't know, it depends on you. There's no rule of thumb like you have to go 5 derivatives. I mean, every problem is its own little thing. You got to just kind of go till you're comfortable. So let's take a look at these. Here they are, right? These are my numbers. All the bottoms, right? All the denominators are just powers of 2, aren't they? Except this one. That one does not fall into the pattern at all, does it? So what will I do with that? Well, I won't even care about it right now, okay? If there's only one that's not following the pattern, I'm not concerned. I can always just peel that off the front of the series, just leave it by itself. So this is 2 to the 1st, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th. So in terms of the derivative, when we take the first derivative, that determines the power on the 2, doesn't it? The second derivative is the power on the 2. The third derivative is the power on the 2. So we should have some connection between the derivative I'm taking and the power on the bottom, yes? What about the numerator? 2 times 3 times 4. Ignore the negative and positive for now. 2 times 3, 2, 1, 1. We said these look like factorials, right? Like this is 4 factorial, 3 factorial, 2 factorial, 1 factorial, 0 factorial. Good, that works. And then if this is 4 factorial, but it's happening at the 5th derivative, it's 1 less than the derivative, isn't it? So like if I'm on the 4th derivative, I only want to do the 3rd factorial. So n minus 1 is something that I'd be using for that. And then I have to look at the fact that it alternates. And again, I'm going to ignore the first one. And I'm just going to look at what? Positive, negative, positive, negative, positive, thinking negative next. We got all that? Now we have to put it together into a formula. Into the Taylor series, which is this. I'll keep all that over there. All right, the Taylor series should look like sum n equals 0 to infinity, c sub n, x minus a to the n, which is c sub 0, x minus a to the 0. plus c sub 1 x minus a to the 1 plus c sub 2 x minus a squared, c sub 3 x minus a cubed. That's just the general formula. And what I'm going to do now is come in and just replace all these pieces with what I have. What is c sub 0? It's natural log 2, right? Right? Divided by what? Don't forget, look. So c sub n is the nth derivative at a over n factorial. Don't forget that n factorial. This number right here is the top piece. The factorial is always going to be on the bottom. So c sub 0 is the 0th derivative at 2, which is this, over 0 factorial. So natural log 2 over 0 factorial, x what? X minus 2 to the 0 power. Which of course that's going to be a 1, but I'm just showing you how I'm plugging in where I'm getting all the pieces. Can I go on? What's c sub 1 for us? It's this number, 1/2, right? Over 1/2 over 1 factorial, x minus 2 to the first power. What about the next one? Negative 1/4, right? I'm going to write it, though, like this. Negative, instead of 1/4, 1 over 2 squared, because that's where I'm picking up that power pattern. 1 over 2 squared, and then over what factorial? Where am I at? 2 factorial? X minus 2 to the second. What's the next one? C sub 3, which one was that? It was 1, 2, it's this one right here? It was 2 over 8, which I'm going to write as 2 over 2 cubed over 3 factorial, and then all that x minus 2 to the third. I'm running out of room. Next one. This right here. So it's going to be positive or negative? Negative. So I've got negative 2 times 3 over 16, which I'm writing as 2 to the 4th, over what factorial am I at here? 4. Does this look like a mess? And x minus 2 to the 4th. One more. Plus, because the next one would have been positive, right? 2 times 3 times 4 over 2 to the 5th over 5 factorial x minus 2 to the 5th plus dot, dot, dot. The numerator is a factorial, yes. That's exactly what I wanted to point out to you, because we talked about this when we saw the pattern. This right here is a factorial, isn't it? This right here is actually 4 factorial. This right here is 3 factorial. This right here is 2 factorial. This right here is 1 factorial, and this one right here is 0 factorial. And then this one right here, this didn't follow my pattern, so it's isolated by itself out here. I'm gonna try and come up with a formula for this right here, right now, with everything from here on. See if you can do it with me. All right, this right here I'm going to rewrite as natural log 2 because that's what that turns into if I replace 0 and, all right, plus sum n equals 0 to infinity. And now let's start talking about this. It alternates. Positive, negative, positive, negative, positive, negative. So I need to start an alternating series. It needs to start with a positive number. So negative 1 to the n, because if n starts at 0, that should do it. Now let's start taking a look at all these pieces here. I've got a fraction on top, which is what? 0 factorial over 2 to the first power, right? So 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial? Just n factorial. Right? Because look, if I start at 0, what's my first one going to be? Positive number, 0 factorial on the top, right? Over what? 2 to the n plus 1. Because look, you want 0 factorial, but you want 2 to the first power. Here you want 1 factorial, but you want 2 squared. Here 2 factorial, but you want 2 cubed. So this is over 2 to the n plus 1. But all of that is over what? 1 factorial, 2 factorial, 3 factorial, 4 factorial, so n plus 1 factorial. I know this looks like a disaster. I'm going to make this a little shorter up there like that. All of this times, right, I've taken care of all this crap that's happening out front. And then it's x minus 2 to what? I want my first one to be 1, right? So how about n plus 1? Almost done. Almost done. I can simplify those factorials because there's an n factorial and n plus 1. So how about we do this? Everyone hopefully understands that this is a fraction divided by a fraction. Fraction divided by a fraction, so I can flip reciprocal. So that's really n factorial over 2n plus 1 times n plus 1 factorial. That's what would happen if you flip that. And then using what we've done before, I peel off an n plus 1 on the bottom with the factorial and then cancel these factorials. So that would leave me with the following Taylor series. Natural log 2 plus sum n equals 0 to infinity. I still have the negative 1 to the n out there. I didn't touch that. But this stuff turns into 1 over 2 to the n plus 1 times n plus 1. And then I have x minus 2 to the n plus 1. This is the Taylor series for f of x equals natural log of x about a equals 2. Any questions? I think it's worth showing you one last thing. This will be the very last thing that we talk about this semester. Okay? And Well, let me do it, and then I'll ask you, does this seem like a problem you would want on the final, or would you want it more as a bonus? All right? So let me show it to you first. There's a background to this story. Have I shown y'all the Bad Professor video? Have y'all ever seen the Bad Professor video? Damn, I wonder if we have time.
Is that you, right? We have about 20, 30, 25 minutes.
Okay, you know what we can do?
Yeah, we have 25 minutes.
We have 25 minutes?
Yep.
Well, I have something to show you still, so, but I'll show you the motivation of this. So if we could get the lights, please. Yeah, let's go. Dark.
Why not?
Oh, gosh. I'm not showing you this because I'm searching YouTube right now, and my goodness, man. The things coming up when you type in worst teacher. There he is. All right, so let me see.
Hyperbolic length, this is 1x, and that is for 2 terms, that is for 4 terms, for 8, and the general solution.
It's only a minute long, so pay
Whatever.
attention, please.
You have the terms written. That is clear? Can you do such kind of drawings?
What?
Can you do it? If you have your homework, do some drawings. It is not asked for you, but do it. And send the drawings. Can you? You have some homework for the next time. Exactly of this kind. Do it. Do some drawing. Okay?
Hold on a second. That's not the one. Oh, here it is. Horrible teacher. All right, there we go.
Going on.
Okay.
It seems that you are not happy.
Okay, let me translate for everyone, okay?
Okay, let's go further.
Okay, so the students go on to laugh and leave comments. The professor's telling them what? In order to do it, you multiply, right? And then the student asks, how do you do it? It can't be done. It doesn't work. And the professor completely blows them off, right? I don't necessarily agree with the professor's approach. However, it's just multiplication, and the student doesn't know how to do it, and the teacher thinks that he's kind of pulling his leg a little bit, like, okay, wait, you don't know how to do this? Like the teacher's confused that a student in that class wouldn't know how to do that operation. So what I'm about to do here right now is an example of that. And this is part of what's in this, at the end of this section. It's multiplication and division of power series. How do you take a power series and divide it or multiply it by something? All right? So you always have to be careful. Can get one more? You always have to be careful. You know, there's a reason why that guy looks like Albert Einstein. He is very brilliant. I don't know who he is, but I'm sure he's a brilliant mathematician. I assure you his mathematics up there is right because he's probably going off of his notes that he's written and they've already been proofed. The fact that the student can't follow him isn't his fault, especially if it's a topic. This is not a Cal 2 class. This is something else, differential equations or something further along. So this is a prerequisite topic that the student is asking him about, right? You understand? Okay. So what I'd like for us to do is I'd like for us to figure out, find the first, that says first, 3 terms of the power series for the function f of x equals 1 over sine x. Which would be the equivalent of me saying to find the first 3 terms of the power series for cosecant x, right? But so what we're going to do is try and convert this into a power series. And we're going to use the fact that we do know what the power series expansion of sine x is, right? The Maclaurin series. It's on our sheet. It is exactly what this would become 1 over. So what's the power series for sine? X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, 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 right? So what I have here is division, don't I? I have division. I have 1 divided by this infinite series, right? Okay. I'm going to look back up here at this guy's work. We're not, by the way, we're not doing the problem that they're doing right there, but I want you to see that if I back up this video where he points to the board right there, I want everyone to see, get over here, 1, boy, you can't see anything down here, 1 divided by an infinite series. Do you see it? That's what the student couldn't do, because he goes from this line to this line, and the student can't follow how that division is possible. And if you look on my YouTube channel, on my playlist, I actually work through that problem and show how it's done, because I thought it was worth working it out, you know? Just look up a horrible teacher on my channel and you'll see me work it out. But okay, so how do we divide this? How do you divide 1 by this? Well, how do you divide old school division, right? Like, what's 13 divided by 4? Well, you did this, right? That's what you did. And that's what we're going to do now. we're going to do long division on this. And on the inside of the division is the 1. Right? And on the outside is the x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. But I can't keep going, right? That thing is infinite. And then we're going to do kind of like we used to do when we had long division here and we had a polynomial and like a polynomial in there. We would try and turn this, usually it was the highest power out here. We try and turn it into this. But because our powers get bigger, I'm going to actually start here. How could I turn x into 1? What would I have to multiply x by to turn it into 1? 1 over x, right? If I multiply x by 1 over x, wouldn't I get 1? And now what we do is we pass the 1 over x through every single one of these. All right? And we write those down below here, and then we subtract. Do y'all remember this with long division? Okay, so let's do it. 1 over x times x gives you 1. 1 over x times this. What is the effect of hitting this with the 1 over x? It brings the power down. The numbers all stay the same. So I'll get negative x squared over 3 factorial. What would the next one be? Plus x to the 4th over 5 factorial. Next one, minus x to the 6th over 6 factorial. And that keeps 7 over 7 factorial. Plus dot dot, and it keeps going, right? And then you're supposed to come through and change the signs. So subtract that row, so that minus 1, or that 1 becomes minus 1, this becomes a plus, this becomes a minus, that becomes a plus, right? Everything changes. And then you add straight down, don't you? So when we add straight down, the 1's cancel, which is what we wanted. And now I go here and here, add down, we get x squared over 3 factorial. Here, negative x to the 4th over 5 factorial. And then plus x to the 6th over 7 factorial. And we go again. What do you have to multiply x by to turn it in to x squared over 3 factorial? X over 3 factorial, right? I multiply this x times x over 3 factorial, I'll turn it into this. So my next term is, keep on switching my blues. X over 3 factorial. And that, if I multiply this times this, I should get this, right? Things are going to start to get kind of ugly here, if they haven't already. Okay? So far, I have the first 2 terms. Do you see I have the first 2 terms? This, the division that we were trying to do, 1 over sine x, that was 1 divided by an infinite series. When I do the division, I have the first 2 terms so far. So I'm just going to have to do this one more time after I come through here. So what is x over 3 factorial times x? That gave me the x squared over 3 factorial, right? This is where things get pretty crappy. What's x over 3 factorial times negative x cubed over 3 factorial? It's negative x to the 4th over 3 factorial times 3 factorial. Just leave it like that. 3 factorial times 3 factorial. We'll resolve this in a second, all right? Y'all see what I'm doing? One more multiplication. Let's do x over 3 factorial times x to the 5th over 5 factorial. What would that give me? X to the 6th over 3 factorial times 5 factorial. And I could keep going, but I'm not going to. And then I come through and change the signs and add down. This becomes minus. This becomes plus. This becomes minus. What's the only one of these things I'm worried about? This one's going to cancel, right? Just this one. Why? That's right. Whatever this turns out to be, that's what I need to multiply x to get, right? So if I can just get this one, I'll know what my next piece up here is. So we got to put these two together. So we better go look at those over here. I'm taking negative x to the 4th over 5 factorial, and I'm adding or subtracting? Adding what? X to the 4th over 3 factorial, 3 factorial. What do those both have in common? X to the 4th. Pop the x to the 4th out then. And I'll put it at the back. I'll have negative 1 over 5 factorial plus 1 over 3 factorial, 3 factorial. Isn't that what it is? I mean, I could go figure out what this number is, but I'm not going to. I'm going to leave it just like that. So that's what belongs right here, right? So what do I have to multiply x by to get this? X to the 3rd, but in front of it, what? That whole thing. Negative 1 over 5 factorial plus 1 over 3 factorial, 3 factorial. So if I take that, I multiply it times x, and then bring it down, and then subtract, it'll go away. You all follow that? These are the first 3 terms. Of course, there's more. Good thing I didn't ask for the first 10, right? Questions? Yes? Well, now let me ask you. Does this seem like a problem that you would like to be able to do, or a problem that you would want to only do as a bonus? Just find the first term? Find the first term. I like that. That's a good idea. All right, well. So no, y'all don't want this? No. Okay. Well, just remember, if you're ever sitting in a class and you're getting mad at the professor because you don't know how to do it, don't come back to me. All right? Remember, you said you didn't want to get into this. So you won't use that in Cal 3. No. Differential equations. Series come up again. They do come up again. But in Cal 3, they don't. All right, so I think we're done. We have 7 minutes. Let's talk about the final. I'm gonna send you out a copy of last semester's final, which was very heavy in Chapter 8. So imagine now, this is what I was telling some other students, imagine that I give you a function and I ask you to find its power series, like from the 8.6, something like 1 over 3 plus x, and I say find the power series for that. Or even worse, it was the one where it was squared and you had to do like a derivative or integrate or something to make that happen. So find the power series, so you go through all the work, you find the power series. I ask you to find the interval of convergence. So you have to do a ratio test, check the endpoints. If I ask you just that one problem, there's like 3 or 4 sections worth of material in that one problem. So I'm imagining it'll be a rather short final, but to focus most of your attention on Chapter 8. Right? I don't know. I don't know. I mean, I haven't written the final, so I can't tell you. It's on Thursday at 12:30. Thursday at 12:30. I'm going to send an email out tomorrow morning that will have what days and times I will be here next week, because office hours are never normal the week of finals because I'm giving finals. And the makeup lecture thing, bonus thing that I've been wanting to offer you. Had y'all thought about Friday, tomorrow?
How many bonus points exactly?
Yeah. I don't know. I'm thinking maybe doing it after the final. Like not immediately after the final. Maybe like Friday after the final type thing. I don't know. I'd like to see how you feel after the final, and if you feel like, oh my gosh, I'm going to need every bonus point I can get, then
It should be on a
you
day
go.
normally classes, because if people have other obligations already, they can't.
I know, but I can't do it during those other times because other finals will be taking place. It's hard to do. It's hard to do any lecture outside of this. It's hard to do.
I think next Friday
So,
would work
yeah.
the best.
And
We got a lot of other classes.
yeah, some people work though, so
What you do is on the morning or in the afternoon?
I think right now everyone should just focus on getting ready for the final. I think that's the most important thing. Look, I've posted all the solutions to all them. I've been really working hard to get all the problems in the homework done so that they're on video for you. I hope you're taking advantage of that. I know that I can see how many people have watched my homework solutions, and you know, there's not many that look at me doing the homework, which is fine, but especially for this stuff, all the little details in there, I advise you to watch it, all right? Now for 8-7, what I would look at, I give you homework last time or no?
Yes.
Did? Well, I didn't for 8-7. I did, no, did I? I did 8-6, right? For 8-7, 5 through 17 is what I've done so far. You should at least do 5 through 17. And you said you didn't really want to mess around with adding or dividing, and so we'll just say 5 through 17. I'll kind of trim it back a little bit. Pardon?
Would you still do some examples of the last problem?
For bonus, you mean like a yeah, I'll put one on as multiplication division. And if you want to look at those in the book, the multiplication, division, and power series are 55 through 58. That's multiplication and division of power series. You're allowed to use this on the final. You're allowed to use the convergence tests. All those convergence tests. You're allowed to use the standard, the packet thing, whatever. Okay, that you're allowed. There is one problem I have to put on the final. The math department requires me to. So make sure you can do a volume of a solid of revolution. Just at least look at that again, like how you find a volume, rotating regions. That'll be on the final, not by choice. All right, well, I guess that's it, right? Adios. See you on Thursday.
Sir, that's Washington